This video will help us to understand how to use the unit circle to evaluate trig ratios and how to find missing angles for trig. Be sure that you've already watched the video on how to fill in the unit circle and are familiar with filling it in both degrees and radians. Now keep in mind that the unit circle is a special circle with a radius of 1 unit. Once we filled it in radians, we got this. And this now marks the position of all the common angles along with what those angle values are. The positions will have the coordinates, for instance, root 3 over 2, 1/2, root 2 over 2, root 2 over 2, and so on as we move across the circle. Now I've got the circle filled in, and I'm going to use it to evaluate. Now in order to evaluate, I've got to remember some basic trig definitions. The sine of theta is y over r, and the cosine of theta is x over r. But keep in mind that on the unit circle, the radius is 1, so we can simplify these ratios. For sine, we would get y divided by 1 on the unit circle, and y divided by 1 is just y. So on the unit circle, sine of theta is just y, and in a like manner, cosine of theta is just x. Now keep in mind this is only for the unit circle, because only on the unit circle will the radius be 1. Alright, let's use this to evaluate. Here's an example. We're going to find the sine of 3 pi over 4 and the cosine of 3 pi over 4. To begin, let's find where the angle 3 pi over 4 is. It's in quadrant 2. Now notice that in quadrant 2, the x is negative and the y is positive. You're to the left of the origin, but above. Because the x is negative, I expect cosine to be negative, but because the y's are positive, it's up top, I expect the sines to be positive. So when I solve this, I'm going to see the sine of 3 pi over 4 is negative, and the cosine of 3 pi over 4 is positive. Alright, let's actually figure out what those ratios are. Here's the angle for 3 pi over 4. I'm going to mark it in purple. The sine will be the y value, which I see in the coordinate, is positive root 2 over 2. The cosine will be the x portion of the coordinate, which I see as negative root 2 over 2. And we can use this to quickly evaluate these trig ratios, and they are exact and very quick. If you use your calculator, you probably are not going to get these exact answers. They're going to be decimals, which won't be as good. Alright, let's try a couple more examples. Let's find the sine of pi over 6 and the cosine of pi over 6. First, find where the angle is. It's in quadrant 1. In quadrant 1, both x and y's are positive, so the sine and cosine ratios of pi over 6 are both going to be positive. The sine will be the y value, which in this case in the coordinate is 1/2. The cosine will be the x value, which in this coordinate is root 3 over 2. Let's try another example. Let's try the sine of 5 pi over 3 and the cosine of 5 pi over 3. Now notice in this time, the 5 pi over 3 is down here in quadrant 4. In quadrant 4, you're to the right, but down, which means the x will be the positive piece, and this time the y is the negative piece, which means the sine is going to be negative, but this time because we're to the right, cosine's positive. Now the sine is going to be the y value, which in the coordinate I see is going to be negative root 3 over 2. The cosine will be the x piece, which in this coordinate is 1/2. Let's try one more example. Why don't you go and try the sine of pi and the cosine of pi? Pause the video for a moment, work it out, and then resume to check your answers. Well, at pi, the coordinate is negative 1, 0. So the sine is going to be the y value, which in this case is 0, and the cosine is going to be the x piece, which would be negative 1. Alright, let's try something other than sine and cosine. Let's try tangent. Now in order to be able to do tangent, we're going to need one more trig definition. Tangent of theta is y over x. Now what makes the unit circle unique is that r is 1. However, in tangent, we don't have r, so we're not going to be simplifying this ratio. It's going to be y over x. But we can use the coordinates for the common angles, substitute in the y and the x values, and then simplify the fraction. Let's see what this looks like. Let's try the tangent of 7 pi over 4. First, let's find where 7 pi over 4 is. It's down in quadrant 4. The coordinate for 7 pi over 4 is root 2 over 2, comma, negative root 2 over 2. Because the y is negative, but the x is positive, when I take the quotient, it'll be a negative. So the tangent of 7 pi over 4 is going to be a negative value. So let's substitute in those pieces. In y over x, the y is negative root 2 over 2, and the x is positive root 2 over 2. Now this is known as a compound fraction. Fractions with inside fractions, and these are tough to deal with. So instead of trying to divide these fractions, I'm going to rewrite it as a multiplication problem. Remember, when you divide fractions, you can multiply by the reciprocal. So I'll take the top fraction, rewrite it, and then multiply, take the bottom fraction, and take the reciprocal of it. That means flip it. So if we do this, we would get negative root 2 over 2 from the top, multiplied by, and then flip the bottom fraction. That would become 2 over root 2. Now this may look difficult, but if you notice, there's things that are going to cancel. Up top we have a positive 2. On the bottom we have a 2. We can cancel those off. We also have a root 2 on the top and a root 2 on the bottom, and we can cancel those. The 2 root 2 over the 2 root 2 will reduce to just 1. Now we still have that minus sign, which means it's actually going to become negative 1. And that's what the tangent of 7 pi over 4 is. Now this is kind of a trick when you're doing something over 4s. On the unit circle, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, notice that the coordinates are always something root 2 over 2's, whether they be positive or negatives. So we need the answer for anything tangent of pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4 is either going to be a positive 1 or a negative 1, and that just depends on the signs. If they're both positives, it's automatically a 1. If they're both negatives, it's automatically a 1. If one of them's positive and one's negative, that's 3 pi over 4 or 7 pi over 4, the tangent's automatically negative 1. It's kind of a quick trick. Now let's try another one. Let's take the tangent of pi over 3. Pi over 3 is at the top towards quadrant 1. Okay, this coordinate is going to have a x value of 1/2 and a y value of root 3 over 2. So when we do y over x, that's going to become root 3 over 2 over 1/2. And again, it's a compound fraction, so I'll rewrite it. We'll take the root 3 over 2, wrap it in parentheses, and multiply it by the reciprocal of 1/2 becomes 2 over 1. This time only the 2 over 2 will cancel, and it leaves me root 3 over 1. Root 3 over 1 is just root 3. All right, let's try one more. This one's a little bit tougher. We're going to take the tangent of 7 pi over 6. Why don't you try working this one out? Pause the video and then check your answer when you're ready by resuming the video. I'll give you a moment. All right, hopefully you tried this. 7 pi over 6 is in quadrant 3. And notice down here both x and y's are negative. So when you take the quotient of a negative divided by negative, it's going to be a positive answer. So I expect the tangent of 7 pi over 6 to be positive. In particular, the y value is negative 1/2, and the x value is negative root 3 over 2. We'll change this into a multiplication problem by multiplying by the reciprocal. We get negative 1/2 times, take the reciprocal of the denominator, and we get negative 2 over root 3. I see that the 2's will cancel, and a negative times negative is positive. I get positive 1 over root 3. Now this answer is not good because we have the radical on the bottom. We need to rationalize the denominator. We'll do that by multiplying top and bottom by root 3's. 1 times root 3 is root 3. On the bottom, root 3 times root 3 is the root 9, and the square root of 9 is just 3. This becomes root 3 over 3. All right, let's try another type of problem here. What if instead we want to find the angle that has a given value? And we're going to look between 0 and 2 pi, which means we're going to look around one complete turn of the unit circle. For instance, I want to know what angle or angles have a sine value of root 3 over 2. Well, sine on the unit circle is the y value, and this value is positive. That means I need my y's to be up top, which means I'm somewhere in quadrants 1 and 2. That's the top of the circle. So look on the top half of the circle, and where do you see y values that are positive root 3 over 2? I see two places. One of them is at pi over 3, and the other is at 2 pi over 3. Now remember earlier in class, we had done problems where we had to find where sines were equal, and we drew problems like this. This is why we did it. It makes evaluating these angles really quick. Looking at the two places where the sine value, or the y value, is going to be root 3 over 2, the angles are going to be theta equals pi over 3 and 2 pi over 3. And that's the answer. Let's try another example. Let's try and find the angles where the cosine value of theta is negative root 2 over 2. Well, cosine is x. Where is x negative? There's two places on the unit circle where you have a negative root 2 over 2 for x. And it's going to be on the left of the circle because that is where x is negative. I see one of them at 3 pi over 4, and the other one is down below at 5 pi over 4. The sketches we did earlier would look like this. And there are therefore two angles that I can use. Theta will be 3 pi over 4 or 5 pi over 4. Both of these have a cosine value of negative root 2 over 2 within one turn of the unit circle. Let's try one more. Try to find where the sine of theta is going to be negative 1/2. Well, sine is a measure of the y values. There's two places on the unit circle where the y is negative 1/2. It's at 7 pi over 6 and 11 pi over 6. So my sketch would look like this. And then those two angles become my thetas. Theta can be 7 pi over 6 or 11 pi over 6. Now we're not always going to look between 0 and 2 pi. Sometimes we're going to have what we call restrictions. Let's look at a few of these examples. Let's find where the sine of theta is 0, but this time instead of looking between 0 and 2 pi, we're going to look at where theta is greater than or equal to 0, but less than pi. Well, where does that mean? If we're bigger than 0, but less than pi, we're somewhere on the top half of the circle. We can be 0, but we've got to be less than pi. So where would the sine of theta be 0? Well, sine is the measure of the y's, so on the top half of the circle, where is y 0? Normally, I'd say it's either on the right-hand side or the left-hand side. But in this case, we have a restriction that says we can be 0, but we can't be pi. It has to be less than pi, which means that one won't count. The only one that's going to work here is the one to the right-hand side, and that's because of our restriction. So we're going to say the answer to this, theta equals 0. Well, let's try a couple more. Let's find where the cosine of theta is negative root 3 over 2, but this time our restriction says that theta is greater than or equal to pi, but less than 2 pi. Where's that on the circle? Pi less than or equal to theta less than 2 pi is going to be on the bottom half. So look at the bottom half, and where is cosine going to be negative root 3 over 2? Well, usually cosine can be negative root 3 over 2 in two places, quadrants 2 and 3, but because we're on the bottom, it has to be the quadrant 3 one that we're talking about. So find that angle, and we'll see that it's 7 pi over 6. At 7 pi over 6, the x piece of the coordinate is negative root 3 over 2. Let's try one more. Let's find where the tangent of theta is 1, and the restriction this time is 0 less than or equal to pi, theta is less than 2 pi. That means we can look in the whole circle. Where's the tangent value going to be 1? Now remember, this is a little bit trickier because this tangent has to be thought of as y over x. How is it you can divide two numbers and get a quotient of 1? Well, to get a quotient of 1, both numbers must be the same. So we need to find where the coordinates match exactly. And to have a quotient that is positive, both pieces have to be positive, or both pieces have to be negative. And I see two places where that can work. It's in quadrants 1 and 3. In quadrants 1 and 3, I see where the coordinates are exact matches. At pi over 4, I'll see that I get root 2 over 2 and root 2 over 2, which when you divide would be 1. And at 5 pi over 4, down in quadrant 3, I see negative root 2 over 2 and negative root 2 over 2, which again, when you divide, would be a positive 1. Because we were allowed to look between 0 and 2 pi, this one has two answers. All right, thank you for watching, and hopefully it helped.